This is the final episode of the PEC GPS mini-series, and we'll go directly into the data reduction coding in Python for the turn regression method. We covered the concepts on part 6, and if you feel like a refresher, the link is down below. Let's dive in!
3, 2, 1, top.
3, 2, 1, half, the Flight Test Engineering channel.
Let's start our data reduction notebook here. As usual, we control the version with the version control. In this case, it's going to be 1.0 initial release. And before we go deep into this, I can show you where you can get this notebook from GitHub to show you the Flight Test Engineering GitHub repository. For the PEC, there's going to be a GPS subdirectory where you can get the notebook and also the data that we collected from the simulator. So if you go into this subdirectory data, you see all the test points that we have collected there. And you can download and follow along if you want. So let's go back to our notebook. And we're going to import the usual libraries, NumPy for the numerical package, Matplotlib for plotting, and in this time we're going to import pandas, which is going to allow us to read the data that we got from the simulator. So let's run this cell here, and I'm setting as well the dark background for Matplotlib so that it matches whatever I have here for my Jupyter Lab environment. Of course, we're running the usual Jupyter Lab with Python 3. We're running Python 3.10.6 at the time of the recording, and this might vary as you see this video in the future. We have the constants and conversion factors already that we saw before, from meters to feet feet to meter, knots to meters per second to knots, Celsius to Kelvin, degrees to radians, and radians to degrees. So let's run the cell as well to load these. And these are the same ISA constants that we saw as well on countless videos before. The temperature at sea level, standard pressure at sea level, lapse rate, speed of sound at sea level, density of air at sea level, R, which is going to be our constant in joules per kilogram per Kelvin, the acceleration of gravity at sea level, gamma, the adiabatic index for air, and then CP. So let's run this as well. And then the data for the airplane, which in our case has a VMO of 350, stall reference of around 105. Of course, it depends, but that's a good value to plot from for our FAR25 verification. And then the instrument errors that I have here for delta VIC for your airspeed indicator, 1 knot, delta HIC 25 feet for your altimeter, and delta TIC for your temperature probe, -1 degree. And our temperature recovery factor for the probe is going to be 1.0. So let's start by loading in some data. And what we have here is just a list of the test point file names that we have in that subdirectory that I showed you. So we have 6 test points, each one has a speed and altitude. And what we have here is just a list that has all the test point file names. Here we created a variable so that we can choose which test point we want to load. So for instance, test point number 5. And here's what loads the data itself. So we're creating a data frame here, which is from pandas, and we're telling pandas to read a CSV, and as an argument for this function, we're passing the name of the file. So how do you get the name of the file? Well, it's TP-1. Why do we have TP-1 for the index of our list? Because in Python, the variables start from base 0, not base 1 as MATLAB. And then we just print the data for that name and print the head of our data frame here. This is going to print the first 5 rows of our data frame and all of the columns. So we have time, PSIM time, altitude in feet, indicated airspeed, Mach number, ground speed, down velocity, east velocity, north velocity, and then a few other columns here that you can have a look later. And then we're going to have, in this case, many rows. Each row is one measurement of these data. So let's start by having a look, and to do that, let's create the vectors with the names that we want to do our data reduction. So ground speed is going to be our Orbis VG dash KT, which is the name of the variable that came in our file. Sigma is going to be our sigma in radians, which is what we have there as well. This is ground track, of course. This is our heading. It's going to be psi in degrees, and we can already transform this to radians because we're going to apply sine and cosine, and all that needs radians. We have our indicated temperature, OAT-C, our indicated airspeed in KIAS, and our indicated altitude in feet. Okay, now that we have our vectors, we can do a quick plot here of our indicated airspeed to see what we're getting. So here we have a plot of VI, indicated airspeed, with symbols plus in color blue, and the label is going to be VI, which you can see here. The X label is going to be sample number, because we're not plotting against time yet. The Y label is going to be KIAS, because that's in knots. This is the title of our graph, flight test data, and we use the grid and plot the legend and then show the graph. So this is the type of data that we're getting from our simulator. And you can see that we have some variation in the airspeed here, 224, 226, so pretty much 2 knots, which prompts us to look at the statistics of the data that we input. So let's have a look to see what type of variation we have. And to do this, we can create a function that calculates statistics for each of the vectors that we want. And why do we create a function? Well, because if we are going to run the statistics for altitude, airspeed, and temperature, and so forth, then we can call the function and obtain the statistics that we want. So what do we have here? We define this function as getStats, and we pass in a data array, which is a NumPy array. And we are expecting the output to be a dictionary. In Python, you start a dictionary, an empty dictionary, with curly braces like this. So our dictionary is called stats. And then we're going to add values to this dictionary, which is a key value pair by each of these lines here. So stats mean, so this is the key mean, is going to be a data array dot mean. So this is going to calculate the NumPy mean. It's going to call the NumPy function mean on this data array that we're passing into the function. And it's going to store this value here under this key, which is called mean. Same thing for the standard deviation. We use this key here to store this value, the minimum, the maximum, and then here it would be very interesting to have an idea of the total variation of our data. So 2, 4, and 6 sigma, which means that we're taking our standard deviation times 2, times 4, times 6, which is going to represent 68%, 95%, and 99.7% of our data, of the variation. And we return stats, which is our dictionary, okay? So to try this out, we can print get stats of what? Of the vector VI. So let's see what we get here. And of course, we get the dictionary, as I said, with the key value pairs. 225.1 with the standard deviation 0.46, the minimum 223.9, maximum 226.9. So you can see it's fairly easy to obtain the statistics for a vector using NumPy. And we can create a better way to plot or to print this output here by saying first what we are printing, airspeed statistics, and then iterating for each key and value in the dictionary that we get when we run the function. So this will run the function, will return a dictionary, and this dot items will return all the key values in the dictionary. And then we just print each key and value. So let's run this. So there you go, you have the airspeed statistics, and you have the mean is going to be such, standard deviation such, minimum, maximum, and so forth. So this is much more pleasant to the eye to look at and understand what's going on, right? Next up, we can run this for all of the data. So we can define yet another dictionary with the data set that we want to run the statistics for example, airspeed and VI, altitude, HI, temperature, TI. Those are the vectors, the key value pairs in this new dictionary. And then we do the same as we did here before. We iterate through all the key value pairs in this data set. And for each key value pair, you print what's the measurement statistics. And then for each measurement that you have, you run the getStats function and iterate through its key value pairs to print the stat name and the stat value. This way you get the airspeed statistics, the altitude statistics, and the temperature statistics. And we can see that from here that 6 sigma for airspeed is going to be fairly reasonable, 2.7 knots. It's not perfect, but for a 360 turn, it's acceptable. Our altitude has 10 feet for 6 sigma, so again, pretty reasonable. And our temperature has pretty much zero variation because, again, this is a simulator. Now we can start the correction and from the Anemometric side. So we're going to do the usual corrections, add our delta VIC, delta HIC, and delta TIC to our indicated airspeed, altitude, and temperature. And we are going to already transform our indicated airspeed from Celsius to Kelvin. And here we can already print the mean values that we get with this corrected vector. And we now find the indicated Mach number from our VIC. And to do that, we're going to start with our VIC and get the pressure ratio QCIC over P0. So next up, we're going to calculate our ISA delta for the, and we add the suffix here, IC, because it includes the position error. So from HIC, we calculate the delta. So delta IC is going to be 0.277. That's the mean value. Of course, we're calculating the whole vector here and here as well. One value for each data point. We find QCAC over PS, and we do that because we have QCAC over P0, and we multiply by P0 over PS to cross out P0. So you get QCIC over P0, 1 over delta. So that's easy because we just calculated both. And now we can find the indicated Mach number from QCIC over PS, right? Same Mach expression that we have used. And now we find the indicated true airspeed. And to do that, we start with the temperature. So first, we use our recovery factor to correct our indicated temperature and calculate what is our ambient temperature. We calculate our theta for the test, since now we have the ambient temperature. Okay, and now we calculate our true indicated airspeed from our indicated Mach number and our theta that we just calculated. Okay, 352.98 true airspeed. And here we recall our wind triangle that we have. We have our indicated true airspeed on this vector. We have our delta VT, which we don't know. This is our error that we're going to find out. This is our true airspeed. Let's say it's the airspeed without error, the true airspeed without error. This is our ground speed that we get from the GPS with its ground track, sigma g. And this is the wind that we don't know as well, V wind, and there's a magnitude and a direction for the wind. So let's see what we're going to do here. So from the GPS side, we get the magnitudes, meaning we get our ground speed, and we get the track angle. So we're going to separate into the east and north directions first, calculating v ground east and v ground north, okay? And remember that we already have sigma in radians, and when we apply numpy sine or cosine to this, this value, we are going to get the correct answer, correct values here for the function. And then we can do a quick plot for our ground speed Orbis. So what are we plotting here? East versus north velocities, ground speed. And again, we're going to plot this as plus signs in blue with the label VG. So let's see what we get. So that's very interesting. We really get an Orbis or a circle here. It looks distorted because the aspect ratio of my screen is not 1:1. It's elongated on the side here, but it looks pretty good. We have seen how we derived everything to get to the solution in our concepts video, and if you haven't watched that, there's a link on the description that you can go and have a refresh. But what's important here is that we need to construct these matrices here, matrix A and C. Matrix A is going to be a stack of ones over a stack of zeros, followed by a stack of zeros over a stack of ones, followed by the cosines over the sines. So let's build this, this matrix here. How do we build this? Well, it's going to be easy. We are going to concatenate a stack of ones, and the size of this vector of ones is going to be the shape of our airspeed vector. We can have a look at what that is if we open a cell here and say vti.shape, what that looks like. It's a tuple of 1521 and dimensions 1. So if we get the first number from that, we get the raw 1521, which is what we want, right? So we're concatenating a stack of ones over a stack of zeros, each one with 1521 elements. Next, we're concatenating a stack of zeros over a stack of ones of the same sizes. And next, we're concatenating all the cosines over the sines, which is exactly what we have here. All the cosines over the sines. So this is matrix A that we build this form, this way. For matrix C, we have to concatenate our ground speed cosine sigma g minus Vt cosine psi test. All of this vector over Vg sine minus Vt sine. So this is how we build the C matrix. It's very similar. We concatenate Vg cosine minus Vti cosine over Vg sine minus Vti sine, right? And now the solution, as we saw before as well, we just use the pseudo-inverse. So for the pseudo-inverse, we're going to again use our NumPy libraries here, and this time we're going to use our PENV from our linear algebra sublibrary of NumPy. And if I just run over here my other browser tab, we can go over to NumPy, and I left this link here on the notebook, and you can read all about this library here directly on the NumPy documentation, right? So let's go back here. So that's how we're getting our solution X as multiplying two matrices. Which matrices? The pseudo-inverse of A times C. Once we have the vector X, which is going to return us v wind north, v wind east, and delta Vt, we can organize its solution in the variables that we have a better name for. So v wind north, v wind east, and delta Vt, and then print them to see what we get. So in this case, we have very little north component for our wind. We have pretty strong east component, and our delta Vt is going to be around 2 knots. Very easy. This is the direct method, but Python also will give you some statistical packages that you can work with and get some more insight as to if your model is being well behaved or not. And one of these packages is Statsmodel. Again, if I just tab over to my other browser here, I have already left the Statsmodels web page here, and you can again read all of the explanations and assumptions that this model will consider when you import this library, right? So here we're going to import that library into NumPy, and we're going to create an ordinary least squares model with this this object here. We're going to tell the package to fit the data, which includes passing the matrices C and A, and because we don't have a constant, we pass the information that has constant equals false. And then we just print the model summary here. So let's run this. What is the null hypothesis here? Well, it is that the variation in the data cannot be explained by the variables we picked, aka wind and delta VT. We have 3 degrees of freedom here. Therefore, if all of these 3 degrees of freedoms from my distribution are 0, it means that we cannot explain any variation in the data with these variables that we picked, x1, 2, and 3. A high F statistics means that there's a high confidence that the model explains what's going on. And our F statistics here is pretty much 7,127. This is shown in another way. The probability of the F statistics, aka the p-value, is low, in our case very low, 0. And if the p-value is less than your significance level, then you reject the null hypothesis. So we would be comfortable rejecting it here. And then we can have a look at each of the variables here. And if we look at the p-values for each one of them, x1, 2, and 3, we see different story, 0, 0, and 0.995, which means that statistically this model is being explained by 2 variables, and the third variable, which is wind north, doesn't explain anything, which is to expect since the wind is from the east. Okay, now that we understand these statistics, we can calculate the wind speed by using our good old Pythagoras friend, by getting the square of our north plus east components and then square root. So we can see that we had roughly 24 knots of wind. And then to calculate the wind direction, we have to correct for the right quadrant that the arctangent delivers to us. So we're going to calculate the arctangent of the east and north components, but we're going to add 2 pi and then do a modulus 2 pi here to get to the correct quadrant. And then to print out, we're going to already transform from radians to degrees and see what we get. We get roughly 270 degrees for our wind, which corroborates with what we had here on our statistics, given that the p-value for the north component is very high, meaning that it doesn't explain anything for this model, right? Like we saw. And now we calculate the correction for true airspeed. So we have our indicated plus our delta VT, and we would have one measurement for each time that we collected data during our simulated flight. But one of the assumptions is that, well, first the error should be constant, but your true airspeed should also be constant as you do the maneuver. Therefore, it's fair to say that we can get the mean of the value. So we can write our true airspeed as our mean for our values plus the delta VT that we just calculated from our statistics. And we're going to get 354.95 knots. Same thing here for the ambient temperature. We can use the mean ambient temperature to calculate, or indicated temperature, to calculate what is the ambient temperature. Okay, we calculate the theta using our ambient to standard sea level temperature. And now we can calculate delta MPC by using delta VT over a square root of theta. And now we have our Mach position error. And at the end, we can calculate the delta Mach as well by doing MIC average plus delta MPC. So this is going to be our truth Mach number, right? Considering this Mach position error that we just calculated. Now for the static port position error, delta PS over PS, we first go from the truth Mach number. We can calculate PT over PA. And then from the average indicated Mach number, we can calculate PT over PS using the same formula. And now we can calculate delta PS over PS using this relationship here. And there you go. This is our delta PS over PS, which was the goal of this data reduction so far. Okay, now that we saw how we get the delta PS over PS, we need to check for compliance with the FAR25, for example. And to do that, we need to expand the data from this pressure ratio down to our delta H and delta V. And we have covered that on part 3 of this series in detail, and the code from here down to the end is exactly the same, and I'm not going to explain it again. You can go back and watch that video if you need a refresh. There's a link in the description that you can follow. But anyhow, let's run all the cells here. They are exactly the same as we saw on part 3. So if we go down to the very bottom and click here, and we can say run all above selected cells. So it's going to run everything again, and you can see here the status. But let's look at the FAR compliance. And if I zoom out a little bit, we can look at the graph, the whole graph on the screen. And yeah, here is the envelope, the FAR25 classic funnel envelope. And we can see that the points for altitude fall outside of the limits. So it's clearly non-compliant in altitude. And if we scroll down to airspeed, well, that's a better story. We are within plus or minus 5 knots in the 5 knots delta band, which shows that it complies in airspeed. We reached the end of this mini-series on position error correction with Python. We learned how to calculate PEC with 3 different methods: geometric and matrix inversion if you only have hand data, and this last one, turn regression with recorded data. This gives you a few possibilities when you're executing your flight tests, and I hope this content was useful for you. Thank you for watching this channel, and hope to see you soon.